write each expression in rational exponent form. So you can see that on number 13, it's in radical form. And so our job is going to be to put it into the other form. The first thing you want to figure out is what's the index. So this one, it doesn't have an index listed. What is in this little like crook though? A 2, right? It's an invisible 2. And so it's a square root, which means that you know, okay, invisible 2, so I would go ahead and put 7xy in parentheses because all of that is in the radicand. It's all underneath the radical sign. And then my bottom of the fraction is 2 because that's what was my index, okay? And then you just have to fill in the missing piece, which is what power would it be in the top? It's got to be something. 1. Yeah, so 7xy, you don't see an exponent, it's raised to the first power. Yep. When I see a 1/2 power, it's a square root. Okay. Let's look at this next one. Again, deal with this index first. The index is, you see it, 3. So that tells me that x minus 2 is, okay, it's raised to a fraction. The 3 goes in the denominator because that was my index. I always encourage you to do that first. And then x minus 2 is raised to a power, right? 2, so that goes in the numerator. Does that sort of make sense? Kind of, sort of, okay? So now we're going to go bop the other way. Write each expression in radical form, so I'm giving it to you as an exponent. The bottom of the fraction on number 15 is 4. That's the denominator, and so that tells me that the index of the root is 4. The base in this exponential expression is 5. So that's what goes underneath. And 5, there's only one more piece we're missing. It's the 3. So we put that on the inside. 5 is raised to the third power. Okay. Now that's a little bit tacky though, because 5 to the third power, you should be able to figure out. This is when you would pull your perfect chart. Do you have one? You could look at your perfect chart and say, okay, my n is 5. 5 to the third is, you could do it on your chart. Or you could do it on your calculator, 5, caret key, 3. 5 to the third is 125. Yeah. So we can write this as the equivalent version of, or maybe I just put, yeah, let's say equals 4 through of 125. 3, because it's a cube root. That's in the denominator, and then we fill in the rest. So the 6m goes underneath, and actually we're going to put 6m in parentheses because that's how it was before. Let's keep it the same. 6m is raised to the second power. You cannot, well, you could leave it like this. That's equivalent, that's correct. But we would want to simplify it a little bit, and Delta Math will expect you to do the same. You actually distribute this exponent a little bit, because you're doing 6 squared and m squared. We could write it as the cube root of, what is 6 squared? 36. So it would be kind of tacky to leave it like that. If you know what 6 squared is, then please tell me what it is. So there you go. All of these 3 forms are equivalent, meaning they all mean the same thing. All right. Let's look at 17, 18. So you see properties of exponents in the right. We'll get there in a second. This one, you're going to go ahead and simplify and then put it in radical form at the end. So you can see we're starting with exponents, and then we'll move it into radical form and see if it can simplify even further. So our first one, we've got 3 to the 5/2 power. Which number here would become my index? 5 or 2? It's the 2. Yeah, it's the bottom number always. So that tells me I have the square root of 3 to which power? To the 5th. Yeah, and again, you can use your perfect chart to evaluate 3 to the 5th, or you can type it in on your calculator. If you're like, I don't know how I would type this in, it's 3. This is the caret key, 3 raised to the 5th. Okay, what is it though? 243. Okay, I'm going to get rid of the index of 2 because we know that's a square root, right? 243. Okay, and here's the thing of the day, and Delta Math makes you do it too. You have to simplify this further. So I have to look at my perfect chart or think with my brain, okay, 243 is a perfect cube. It's not a perfect square. And so what's the largest perfect square that 243 divides by? Or you could do that thing where you like do prime factorization. What's the largest perfect square? 81. I think, check that for me. 243 divided by 81. Yes? I think so. 81 times 3. Yeah. And so we can break that down a little bit. Since this one is perfect, we can evaluate it. The square root of 81 is 9. So it becomes 9 root 3. So here's the thing of the day. So you have to switch it over to the other form and then give me, like, simplify it further if you can, which most of them will, okay? This next one's a little bit weird, and then we'll probably just pick one from each section on the rest. So let's see, negative 32 raised to the 3/5 power. The denominator gives you the index. What's my denominator? 5. So that means it's the 5th root of, okay, we're using negative 32. You can imagine if you put negative 32 to the 3rd power, if you type that in your calculator right now, it's going to be like a really obnoxious number. So actually, we don't want to do this. This is not good. We don't want to put the 3 on the inside. It would be much better to put it on the outside, because if I notice that that's going to give me a terrible, really big number, we don't want to do it. And so it's fine when it's like 3 to the 5th, but if it's negative 32 to the 3rd, yikes, it's not going to be fun. The good news is you can use your perfect chart to evaluate that. 5, the 5th root of negative 32. Yeah, the 5th root of 32 is 2, which you can use your chart. We would get then negative 2, because it's an odd root, so it looks like this. So we switched it over. I'll use an arrow when I switched over. Switched over to radical form, and then the 5th root of 32, negative 32, is negative 2, and that gets raised to the 3rd. You could type it in your calculator. Again, use your perfect chart. Negative 2 to the 3rd is 8. Yeah, so 2 to the 3rd is 8, and it's negative times a negative times a negative. So it's going to still be negative because it's odd. So it's actually just straight up negative 8. So you have what from this? 1, 2, 3. These are all equivalent. If I'm taking the EOC would ask, like, select all that are equal to that. And you would have to pick all of them for my freshmen and sophomores in the room, okay? Okay, I'm not going to do all these examples, and nobody got time for that. Let's look at just a couple. Both of these here are examples of when you have to add your exponents, both 20 and 19. But I'm just going to do the one on the right, okay? Just for the sake of time, since we've already spent 2 days on this. I can go ahead and multiply 3 times 2, like normal. 6, right? Okay. The y has no friends, so here he goes. And then you have to add your exponents, because I'm multiplying, and it doesn't really look like multiplication, but it's side by side, so it is. I'm going to add these two exponents, x squared and x to the 1/3. So you could use a calculator or you can use your brain, but you need to add your exponents. And if you have a calculator you're comfy with using fractions, you can use it. Otherwise, you could use Desmos. Yeah, it's 7/3, so 6y and then x to the 7/3 power. All right, and now we're going to switch it over into, so I'll draw an arrow. We're going to switch it over into radical form. You'll notice that 6 and y are not raised to that power. It's just the x. And so we say, all right, what's the index? It's the bottom number, 3. So it's the cube root of x to the 7th. Okay. So you do the exponential rule, you switch it over into radical form, and then the fun doesn't even stop here. Can you believe it? You now have to simplify the radical, which we did, I don't know, a couple days ago. We ask, okay, can 7 divide by 3? Or can 3 go into 7? How many times can 3 go into 7? 2 times, right? Not evenly, because you'll have a remainder of 1, right? There'll be x to the 6 with 1 left over. So then we can do it like this. So final answer here, 6y. X, you said it can go in 2 times. So x squared. And then you would have how many remaining? 1, x to the first. You don't really need the x to the first, but it is technically correct, so I'm just going to leave it. Okay. It's a lot. All right, so go ahead and write that down. We are going to skip, and I'm not going to do 21. I'll do 22, so I'm going to do the more difficult one. Okay, you can see in number 22 that 5 does not have an exponent. But it does. When you don't see an exponent, it's a 1. So it's 5 to the first, and then x to the 1/4. And then you literally have to just multiply these exponents, or you can think of it kind of like distributing. So it would become 5, and then 1 times 2 is 5 squared. And then here I am multiplying these. So 1/4 times 2, you multiply the top of the fraction. It is 1/2. I'm going to write it as 2/4 for just a second. And then that is equivalent to 5 squared is, oh man, don't let me down. 25, and then 2/4 becomes 1/2. So you multiply your exponents, and then you look for, okay, I got to switch this over to radical form. So the bottom number is 2, which means I have a square root. 25 is not taken to the square root, fun fact, just the x. So it looks like this, the square root of x to the first. Okay, and I'll highlight the index again so you can see where that number went. Okay, this looks a little bit weird, and so typically we would just write it as this, 25 times the square root of x. Okay? Wow. And you can't simplify that, and I know that because you can check it over here. Can 2 go into 1? Absolutely not. So he's done. When I have division, I subtract my exponents because I'm like canceling them out. And so if we look at number 24, you see 6 divided by 3. So we're going to go ahead and just do that as normal. That would be 2. And then you subtract your exponents. So it's going to be a, and then you're going to subtract 7/3 minus 2/3. Oh man, common denominators. You can do it. 5/3. So 2a to the 5/3 power. And then you guessed it, you have to flip it over now into radical form. So I'll draw like an arrow to show I'm going to switch it over. The index is going to be 3. So it's the cube root of, is 2 raised to the 5/3 power? No, just the a. So 2 times the cube root of a to the 5th. That bottom number becomes an index, and then you just try and simplify it. I think we may have done one like this earlier. If I'm doing the cube root, then I'm saying, okay, how many times does 3 go into 5? Once, right? And then you would have a remaining. 3 goes into 5 one time with a remainder of 2. So then it looks like this. So 2a, what would that be, to the first? And that's because of this. If I try and divide the exponent by the index, I would have 2 left over, so then it's still the cube root of a squared. Wow. And that's a simplified version all the way. So if we're on like a multiple choice test, can I ask which of these is equivalent? Well, 2a to the 5/3, 2 times the cube root of a to the 5th, 2a times the cube root of a squared. They're all equivalent. You could select any one of them. Or if it's select all that apply, you want to try and catch them all. X to the negative 4th power. Then I would want to say, okay, he can't stay here. I got to move it to the other side of the fraction to make it positive in order to be done simplifying. So it would become 1 over x to the positive 4th power. And then any empty spots fill with a 1. So here's another example for you. Let's say they're both on the bottom of a fraction like this. This time I have like x to the positive 3, but y is raised to the negative 5th power. Then remember this one has to move. Just the one that's negative has to go up. And so then the x to the 3rd gets to stay. So it would look like this. Y to the positive 5th over x to the positive 3. That one, other one gets to stay because it's a positive exponent. Just a refresher for you.